So this is my series of slides that discusses the stability of transition metal complexes and the factors that affect the stability of transition metal complexes. And one of the reasons why we want to look at what makes a more stable transition metal complex is to better understand some of the reactions that occur, how you can design synthesis, and why some reactions or some products form over others. So the most common way of defining the stability of complexes is with the equilibrium constant associated with the formation of that complex. If you'll remember from Chem 1b, this is the formation constant. So here we've got a reaction that we're looking at, and so this is the copper complex with 6 water molecules attached to it, and we're going to displace one of the waters with a amine ligand. So if we look at this reaction, the formation constant, remember it's products over reactants, so our product is the copper complex with 1 amine and 5 waters bound to the copper over the initial reactants. And this reaction, the equilibrium constant for this reaction is 2 times 10 to the 4th. So this means that the equilibrium lies heavily to the right. And so this gives us a large value. So if the equilibrium lies heavily to the right, this means that we have a more stable complex. So the larger the K value, the greater the stability constants. So here we want to compare the overall versus the stepwise stability constants. So the stepwise are the individual steps that lead to the overall reaction. So in this first reaction, we have 1 amine replacing one of the water molecules. And then we can replace another water molecule with the second amine and then complete this reaction until we have all of 6 water molecules replaced by 6 amine ligands. So notice that the individual equilibrium constants varies for each step. And we can kind of relate this to the statistic. So here in this first reaction, we've got 6 sites for water to be displaced, creating a vacant coordination site for the amine to come in and replace one of the waters. So there's 6 possible places that it can happen. So the equilibrium constant for this reaction is 2 times 10 to the 4th. Now, on the next reaction, one of those 6 spots has already been occupied by an amine. So we only have 5 spots to choose from that the amine can replace one of the water. So notice that the equilibrium constant for the second step is smaller than the first. And as we go down, even to the last step of this reaction, notice here on this last step where we have one last water molecule to be replaced by an amine, there's only one possible site to replace it. Now, yes, of course, these other amines could be replaced by this other amine, but it results in the same complex. But if we replace this water with this amine, there's only one site to it, and so the possibility of this happening is very small. So the equilibrium constant is very small. Because remember, too, these reactions are reversible. This could easily lose one of its amine and get replaced with one of the waters that was released into solution. But lots of times we're interested in just the overall formation constant for the reaction. So the overall reaction would be going from this copper hexaquose species to the copper hexaamine species. And we can express the overall formation constant as the beta value. So it's often called the beta for the overall formation constant. So the overall formation constant for this series is 5 times 10 to the 12th. And remember, so if we were to add up all of these reactions to get the overall reaction, we have to multiply the K values. So this is how we get this beta value of 5 times 10 to the 12th. So this, remember, represents the equilibrium constant associated with the overall reaction. Now, that log value, that 5 times 10 to the 12th is a very large value, so it's very difficult to work with sometimes. It's not as easy to work with. So because formation constants can be rather large, many times you'll see them expressed as logs. So rather than just saying the beta value of 5 times 10 to the 12th, it'll be the log beta. So the log beta value is 12.7. And if we remember our rules of log, so rather than here where we're multiplying the k values, here we're adding the log of the k values. So this has to do with the rule of logs. Now I want to look at trends in overall stability constants. Here we've got a mercury complex that is octahedral, so you've got 6 water molecules bound to the mercury complex. And we're going to replace one of those aqua ligands with a chlorido ligand. So it's simply just a substitution reaction for one of the waters with the chlorides. And the log value, log K of this first step is 6.74. And if we replace another water molecule with another chloride, we've still got an octahedral complex, and log value, log K for this step is 6.48. Now notice in this next step where we're replacing another chloride ligand, we start off with the 6-coordinate mercury complex. Now we're going to a 4-coordinate mercury complex. And you see the big jump or the big change in the log K values? Yes, it's still decreased, but there's a big, huge change or difference where we only changed by 0.3 log units. Well, here's we're changing by about 6. So if we kind of look at this reaction, here we're starting off with this mercury complex with the 2 chloride ligands and 4 water molecules. So this is an octahedral complex. When we add that 3rd chloride to the complex, notice how we go from an octahedral complex to a tetrahedral mercury complex. So this is why looking at some of these stepwise formation constants can give us some information about the mechanism that something different has happened. So this is, an interesting thing to see when you're studying some of these formation constants of these complexes. So this large deviation from the trend indicates a significant change in structure. Now also when we're looking at the overall stability constants, remember that the stability constant, that log K, those equilibrium constants are related to the delta G. So the delta G equals negative RT ln of K. So remember, so the larger that K value, and you got the negative out in front, the more favorable the reaction is. And you also remember that the free energy value, that delta G, remember negative values are spontaneous reactions, are also related to the enthalpic terms of a reaction. So it has to do is with bond energies and bond association energies and formation of bonds, but it also has to do with entropic effects, so the entropy associated with a reaction. So what I'm trying to get you to see here is the relationship. There's a relationship between the equilibrium constants, so those stability constants, those formation constants, and there's a relationship between entropy and the enthalpy terms. But just a reminder for what we saw from this data, that the reversal or large deviation from stepwise K trend values, that indicates a significant change in structure. So that was one of the 2 main points of this slide. So we're going to look at some factors which affect the stability of transition metal complexes. And this was put together by Paul Lindahl. He's been one of my mentors in inorganic chemistry. And I just felt that this list was very useful to me when I was studying inorganic chemistry for understanding some of the generalized trends, so that I didn't have to memorize as much. But I could also make predictions as to whether or not a complex would form, or explain why some reactions would take place over others using these 9 factors. So we'll look at all 9 of these, but I'm going to break these series of slides up, and in the first set of slides we'll cover 1 and 2, and then we'll pick up with Jahn-Teller effects for the second series of slides and cover through the pH of a solution, and then with the third recording we'll cover denticity of ligands and the chelate effect, the size and bulk of ligands, and the macrocyclic effect. And so I'm just breaking up these files. So I'm just breaking up these files so that they're not so large, but there's 3 files associated with this lecture series. So the first thing that we want to look at is things that affect the stability of transition metal complexes, the size and the charge of metal ions. And this is based on the Irving-Williams series. So they found that if we're using a metal in the 2+ oxidation states, and we're using typical ligands like sulfur, nitrogen, or oxygen donor ligands, the stabilities generally increase from left to right as we go across the periodic table. So with everything else equal, metal ions with smaller radii and higher charge are going to yield a more stable complex. And this is because electrostatic interactions are so important. So think about this. Remember, we are looking at metals which typically have a positive charge, and we're adding, that's our Lewis acid, and it's going to accept electron density from our Lewis base. We get that Lewis base addict interaction. And so remember, this is not truly a covalent bond, this is not truly an ionic bond, but there's some ionic character and some covalent character mixing in to make these coordinate covalent bonds. And the stronger your metal complex is, the stronger that Z effective. So we just generally see the increase in the Z effective as we go across the periodic table, that you're going to have that increased charge to better hold on to the electron density donated by the ligand. And we can see this illustrated going from barium all the way across to copper. But with the Irving-Williams series, you have to be careful because there is a switch, there's a reversal when it comes to zinc. Yes, it increases as you go across, but at zinc you don't see this, it bucks the trend. And this is going to be, we can explain this based on ligand field stabilization energies. And that'll be our second item that we'll discuss that affects the stability of transition metal complexes. So we'll come back to that. So here we have some data showing how the size and charge of a metal affect the formation constant. So here we've got the log Kf, so the higher the value, the more stable the complex is. And here we have this oxalato ligand, so we've got these 2 oxygen donor atoms that combine to the metal. And we're starting off with barium, strontium, magnesium. So as we go across, when we're going across the periodic table, we see that we have an increase in the formation constant. And we max out at copper right here. But when we get to zinc, we have a decrease in the stability of that complex. So it's reflecting this trend. So the general trend is that as you go across the periodic table, Z effective is increasing. So this is going to create a more stable metal complex, but we have some exceptions when it comes to zinc. Now the second term that we'll be looking at is the ligand field stabilization energy. So we abbreviate this the LFSC. So if you remember, we talked about ligand field theory and crystal field theory, and that model of how d orbitals interact and overlap with the orbitals on ligands, and how it affects the splitting of the d orbitals, and how that when d orbitals are complex when the metal is complex by ligands, those orbitals are no longer degenerate, they're no longer the same energy value, they start to split, and that'll be determined based on their geometry. And the ligand field stabilization energy, this is a measure of the net energy of the d orbitals relative to their average energy. So if a complex has some ligand field stabilization energy, it has some extra energy gained when those orbitals split compared to when they were not split. So that average energy before the ligands were attached to the metal center. So we're comparing to that Berry center. And the calculated value depends on the different order of the d orbital energy. So remember when we did the crystal field splitting diagrams for tetrahedral and octahedral and square planar, we had different splitting arrangements of the ligands. So that's where they're talking about you get different values because those are split differently. Now these ligand field stabilization energy values, they're relatively small with respect to the average energies of the d orbitals. So it's not a huge factor, but it is a contributing factor to the stabilities of some complexes. So here's where we can define the ligand field stabilization energy. So remember, in the absence of a ligand field, all of these d orbitals are degenerate. So they're all the same energy value. And then when we put them in the presence of an octahedral field, those orbitals then split. So the XY, the XZ, and the YZ all go down in energy because those are stabilized because you don't have good overlap with those orbitals with the ligands. But in an octahedral complex, remember the DZ squared is going to have very good overlap with the axial ligands. And the X squared minus Y squared are going to have really good overlap with the equatorial ligands. So those are destabilized. So those are going to go up in energy. And the ligand field stabilization energy is a combination of the stabilization of the electrons that are going down added with the energy of the electrons that are destabilized by going up in energy. So those that go down in energy, those go down in the octahedral by -2/5 octahedral. So you can think of this as being divided into 5 parts. There's 2/5 of this separation down, and these two go up by 3/5 of this splitting value. And when you calculate the ligand field stabilization energy, so if we're looking at X is the number of electrons in the destabilized orbitals. So those electrons that are up here, so these have been destabilized. So the number of electrons in here times 3/5 minus the number of electrons in the stabilized orbitals times 2/5. So that's how we calculate the ligand field stabilization energy in an octahedral field. Now in a tetrahedral field, remember that the ligand field splitting diagrams are these are reversed compared to the octahedral, where the X squared minus Y squared and the D squared go down in energy, and these go down by 3/5 delta tetrahedral. So the delta tetrahedral is the change in energy between the difference in energy between the lower levels and the upper levels of these d orbitals. And the XY, the XZ, and the YZ go up by 2/5 delta tetrahedral. So the units, when you're talking about the ligand field stabilization energy, whatever this value that you calculate is multiplied by the delta value. So delta tetrahedral for the tetrahedral complexes or delta octahedral for the octahedral complexes. Now, when we're filling in the electrons for complexes, they can either go in what we could term a high spin arrangement, or they can go into a low spin arrangement. So in the high spin, this means they have a high spin value. And spin, the spin value is equal to 1/2 times the number of unpaired electrons. So in this case, in the high spin case, the S value is, so we have 1, 2, 3, 4 unpaired electrons, 4 times 1/2. So the spin value is 2. Now let's compare this to the low spin case. In the low spin case, all the electrons are paired up. So we have no unpaired electrons. So the spin value is 0 times 1/2. So the spin value is 0. So this has a low spin value. So the spin is low. Here the spin has a higher value, so it's a spin of 2. So it's not just that you have electrons up high that makes it high spin. It has a high spin value. And here the electrons are all down low, so that's a low spin value. It has to do with the spin value. Now, what requires the least amount of energy. So that's what we're looking at when we're trying to figure out whether or not something will go high spin or low spin. Notice in the high spin case, the separation for the delta octahedral here is smaller than that of the delta octahedral here for the low spin case. So in a high spin case, what we're looking at, you've got a smaller energy gap. So what this is telling us is that it takes less energy to promote one of these electrons to the higher orbital value, the higher orbitals, compared to pairing up these electrons. So the gap is small, so it's easier to promote the electron than it is to pair it up. But when we're looking at the low spin value, because remember these are both a d6 arrangement, so both of these have 6 electrons. The low spin value, it takes less energy to pair them up. You have, because remember there's repulsions for putting 2 electrons in the same orbital. So you've got repulsions that are happening, but the repulsions, the energy it takes to pair those up is smaller than it would be to promote one of these electrons into one of the higher orbitals. So low spin cases, the separation is very high, so it's easier to pair the electrons up. In a high spin case, the separation is small, so it's easier to promote an electron than it is to pair the 2 electrons. And so this is what we're looking at. We're talking about high spin versus low spin. And we can actually tell the difference spectroscopically using several different techniques. But one of the easiest ways is to determine how these complexes interact with the magnetic field. Because in this case, we've got 4 unpaired electrons, so this complex would be paramagnetic. So this complex should be attracted to a magnetic field, and it should be a fairly strong attraction to the magnetic field. But this low spin, all the electrons are paired, so this is a diamagnetic complex. So if we were to put this into a magnetic field and measure the magnetic susceptibility, this complex would repel the magnetic field very weakly, and so we could determine that this complex is diamagnetic and this other complex is paramagnetic. Now the splitting of these d orbitals depends upon 4 factors, and these are crucial for helping us decide whether or not something will be high spin versus low spin. And the first that we want to look at is the identity of the metal. Typically your second or third row transition metals are more likely to have a greater splitting of the d orbitals. Those are capable of splitting those d orbitals more strongly than the first row. And you typically see about 50% greater splitting for second row than you do first. And you still see a greater separation with the third row compared to the second row, but you're not seeing as big of a drastic of a change. But definitely with the second and the third row, the splitting is much greater than with the first row of the metals. Now the type of metal isn't the only thing that's important, it's the oxidation state of the metal as well. A lot of times in the inorganic lab, we'll look at several complexes, and we'll look at different oxidation states of the metal. And metals with a higher oxidation state are stronger. They can pull those d orbitals apart even more. So the higher the oxidation state, the greater the splitting. So if we were to compare an iron 3 complex with a very similar iron 2 plus complex, the iron 3 should have a greater splitting between the d orbitals, and we can either see that spectroscopically through the colors, or we may see a change from high spin to low spin. So the first 2 things we looked at, we've focused on the metal affecting how the d orbitals split. It's not just the metal, it's also the ligands that are attached to the metal. So our third thing that affects the splitting factor is going to be the number of ligands. The more ligands there are, the greater the splitting. That's why when we showed you the tetrahedral complex, which only has 4 ligands, that had a smaller splitting, smaller delta value than the octahedral complex, which has 6 ligands. This is why tetrahedral complexes are always high spin. It's because there's fewer ligands to split those d orbitals, so those complexes are always going to be high spin. But with octahedral complexes, if you've got more ligands, you also need to consider some of these other factors when trying to predict whether or not something will be high spin or low spin. Okay. Now, it's not also just the number of ligands, it's also the nature of the ligands. So different types of ligands split the d orbitals differently. And this is where we use the spectrochemical series. Now, the spectrochemical series was experimentally determined. They just made a bunch of complexes using the similar metal center, similar oxidation state, and just varied the ligands to see how that affected the d orbital splitting. And what they found was that typically pi donors are very weak. They call them weak field ligands. They don't split the d orbitals very much. So if they don't split the orbitals very much, you're much more likely to have high spin complexes. And those that have good pi acceptor abilities are much stronger field ligands. Those are so stronger so they can pull those d orbitals apart much more easily. And so you get a greater separation. So the greater the separation between those d orbitals, the more likely you are to have a low spin complexes. So like an iron cyanide, like ferricyanide, or other carbonyl complexes, you're likely to see low spin complexes. Now, there are weak pi donors. Those weak pi donors are going to split the field more than the pi donors. And then those with no pi fix, so the nitrogen-containing ligands, are going to be in between the weak pi donors and the pi acceptors. So this general trend of the spectrochemical series of halides being pi donors, oxygen-containing ligands are weak pi donors, nitrogens have no pi effects, and cyanide and CO are good pi acceptors. That's something you should memorize and have in your repertoire for understanding the spectrochemical series. Now, if you were to need something more complex that shows things within that series, so maybe like the ethylene diamine is a stronger field ligand than amine, that's not something I think is important to memorize. If you needed that kind of information, I would give you this more expanded series. But you should have a good idea that pi donors are weak field ligands, and we increase the ability of those ligands to separate these d orbitals with the weak pi donors, then the ones with no pi effects, and then the ones with pi acceptors. Now, if we were to look at the molecular orbital diagrams of these complexes with these different types of ligands, we'd be able to better see how the pi acceptor ligands affect the separation, why they cause a bigger separation than the pi donors. And I think I had that in another slide for you in another series. So here we have some data to back up those ligand field stabilization energies. Now here's a graph where we're looking at the predicted values of the delta H of hydration. So hydrating, putting water molecules on these metals in the 2+ oxidation state. So these are the predicted values. So these are the delta H values. And as we go up, we have more negative delta H values. So this is going to contribute to more negative delta G, and a more negative delta G is going to result in a larger equilibrium constant, so it's more stable. Now notice that for a calcium 2+, a calcium 2+ is going to be a D0, so you have no D electrons. And if you don't have any D electrons, the experimental and the predicted value match up very well. But if we start looking at, let's go to the vanadium 2+. The vanadium 2+, that's a D3, so you've got 3 electrons in the D orbitals. Let's pull up my little pen. So we got 1, 2, 3. So we have 3 electrons that were stabilized by 2/5. So this gives us a value of -6/5. So this is the same as -1.2 delta octahedral. So we get some extra stabilization, so more stable, the more negative the delta H value is due to this ligand field stabilization energy. Now let's compare this to manganese. Now with these metal complexes and the hydration values for the 2+ oxidation state, for these first row transition metals, and water being the ligand, these are always high spin. So if we're looking at a manganese 2+, this is a D5. So at 1, we're going to have our 5d orbitals. We've got 5 electrons. We're going to the high spin configuration. 1, 2, 3, 4, 5. So we're looking at this data point right here. Notice that 3 of the electrons got destabilized by -2/5. And these other 2 electrons were destabilized by 3/5. So if we were to add this up, we get no ligand field stabilization energy. So notice that when we have no ligand field stabilization energy, the predicted value and the experimental value are the same. So this deviation from this trend, this extra stability, so this more negative delta H value is due, we can contribute this to the negative, increased ligand field stabilization energy. As you can see, as we maximize our ligand field stabilization energy here with nickel, -1.2, but as we go to copper 2+, 1 over, you're putting another electron into a destabilized orbital, so we're going to lose some of that ligand field stabilization energy. So the copper doesn't get as much ligand field stabilization energy as the nickel. So the difference in energy here is smaller than it is here for the nickel. But yet the copper complex is still more stable. And remember, this has to do with the increase in the Z effective. But remember when the previous slide when we talked about the zinc complex not being as stable as the copper? It's because the zinc doesn't get any ligand field stabilization energy. Because the zinc 2+ is a D10, and if we're looking at D10, let's draw orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we calculate that ligand field stabilization energy for all of those, it doesn't get any ligand field stabilization energy. So the combined effects of the increased Z effective and the ligand field stabilization energy make the copper 2+ complexes more stable than the zinc 2+s. Okay, so I'm going to stop this presentation here and create a new recording just so that the file sizes are not too large.